Good morning, good evening, good afternoon, depending on where you're joining us in the world. Welcome to Nano Explorations, our twice weekly celebration and conversation and engagement with the phenomenal research of our students that's happening at MIT as part of MIT.nano and across the campus. Today it's my great pleasure to introduce Diana Wofk, who just completed her master's in the Department of Electrical Engineering and Computer Science. She's graciously joined us to share her work in fast and energy-efficient monocular depth estimation on embedded systems. Diana, thank you for your time today, and I look forward to hearing about your work, and I'll turn it over to you. And participants, please save your questions and where you can raise your hand or put your questions into the chat. With that, Diana, it's all yours.
Hello, everyone. My name is Diana, and today I'll be presenting about my work on fast and energy-efficient monocular depth estimation on embedded systems. This work was supervised by my advisor, Professor Vivian Zee, and was done in collaboration with Fengchang Ma, Dianyu Yang, and Professor Sartesh Karaman. I'd like to start out by highlighting several different applications of depth sensing, an active area of research in computer vision. This is a key step in autonomous navigation, for example, of drones or small robots that could be deployed for search and rescue or disaster relief missions. Depth sensing is similarly important in navigation systems within self-driving cars. More recently, depth sensing has also seen applications in biometric security, with three-dimensional depth scans of facial features being used to unlock devices like phones and computers. There are several different methods of depth sensing, and they can be classified in these groups. We have stereo vision, where depth information is extracted by comparing object locations in a pair of images taken by two cameras that are separated by a fixed length. We also have time-of-flight cameras, where depth estimates are measured based on the round-trip time of an emitted and reflected signal pulse. An example is LiDAR, commonly used in self-driving car technology. This sensor scans environments with laser signals. Lastly, we have structured light cameras that project light patterns onto surfaces to produce three-dimensional maps of them. Many of these sensors face limitations in their range and resolution and tend to be bulky with high power consumption. This has motivated research into monocular depth estimation, where a dense depth map is determined from just a single camera image. This is appealing due to the ubiquity and the low cost and size of RGB cameras. Let's narrow down now to one particular application of depth sensing: autonomous navigation of low-power miniature robots. A camera on board one of these robots would take an image, and from this image, a depth map is generated. The pixel-wise depth estimates can then be used for obstacle detection algorithms and motion planning. The challenge here is ensuring that depth estimation is accurate and energy efficient. If the algorithm is inaccurate or too slow, the robot will misinterpret its environment and crash into an obstacle. If the algorithm is too power hungry, the robot may simply run out of energy before getting to its destination. Our work investigates deep learning-based methods for monocular depth estimation, as many state-of-the-art approaches are learning-based. These algorithms use deep neural networks to estimate depth for every pixel in an input image. Depth estimation neural networks typically consist of an encoder-decoder type structure that I will describe in more detail shortly. When deploying our depth estimation neural network, we target several embedded platforms, including the NVIDIA Jetson TX2 CPU and GPU, the Apple iPhone, and an embedded FPGA part of the Ultra 96 system on chip. Let us now explore the structure of a depth estimation neural network in more detail. The network consists of two smaller subnetworks, an encoder and a decoder. The job of the encoder is to extract information from the input RGB image. For instance, features like corners and edges. This is very similar to what is done by image classification networks. The low resolution features from the encoder are then directly fed into the decoder, where they are gradually upsampled and merged together to perform a high resolution depth map output. The encoder and the decoder may be linked even further through skip connections. These pass additional feature details from the encoder to help improve the clarity of the feature maps that are processed within the decoder. This often leads to a sharper depth output. There are different ways in which features passed along these skip connections are merged within the decoder. For example, the features may be concatenated, resulting in a larger feature map, or they may be added pixel-wise, maintaining the feature map size. In existing depth estimation neural networks, the encoder is often based on an image classification network that may be deep with numerous layers. Decoders are often custom designed and tend to consist of complex building blocks. For instance, an individual building block may contain multiple convolutional layers, which will increase the decoder size and complexity as more of these building blocks are added. A larger number of layers in the encoder and the decoder allows state-of-the-art models to achieve high accuracy rates in depth estimation. However, these models are also too large and too computationally heavy for real-time inference on devices with resource constraints. The most common type of layer found in depth estimation neural networks is the convolutional layer that performs two-dimensional convolution on an input feature map. Each such layer contains a number of filters dependent on the number of feature map channels processed by that layer. In a standard convolutional layer, if there are C input channels and M output channels, the layer computation involves C times M filters. The height and width dimensions of the filters are typically a small odd number, such as 3x3 filter or a 5x5 filter. Efforts to design more compact deep neural networks have included developing computationally simpler convolutional layers. One example is the Depthwise Separable layer, which splits the standard convolution into two. A depthwise convolution that operates on a channel-by-channel basis, this convolution uses filters that have a height and a width of k and are a single channel each. And a pointwise convolution that scales and sums pixels values across channels. This convolution uses filters that are multi-channel, but they have a height and a width of 1. The net effect of this depthwise decomposition is a reduction in parameters, due to there being less filters to train. The resulting deep neural network is less computationally costly. The Depthwise Separable convolutional layer was introduced as part of the MobileNet family of image classification networks. And this layer is heavily incorporated throughout our own depth estimation neural network. Our depth estimation DNN is shown here. The input here is a 3-channel red, green, and blue image of resolution 224 by 224 pixels. The output is a single-channel dense depth map of the same resolution, 224 by 224. We adopt an encoder-decoder structure with low latency designs for both. Our encoder, shown in blue, is based on the compact and computationally simple MobileNet network that utilizes depthwise separable layers. Our decoder, shown here in yellow, consists of 5 cascading upsample layers. Each of these upsample layers performs a single 5x5 convolution that is followed by nearest neighbors interpolation. This decoder design differs from complex decoder designs in previous works that may incorporate multiple convolutions per upsample layer. Furthermore, we perform convolution before interpolation as opposed to after. This allows us to reduce computation in each upsample layer by a factor of 4. The bar chart on the bottom shows the progression of runtime improvement that we observe in our design. The runtimes shown here are in milliseconds on the Jetson TX2 GPU. Our baseline here was selected to be a model achieving state-of-the-art accuracy rates on monocular depth estimation at the time of this work's publication. This baseline model consists of a deeper encoder network based on ResNet 50, paired with a more complex decoder using 3 convolutions per upsample layer. The decoder dominates this model's runtime and does not allow for real-time inference. In comparison, our model, shown to the right, achieves a reduction in both encoder and decoder runtime. We further modified the decoder to utilize depthwise separable convolutions in every upsample layer. This allows us to roughly half the model runtime, and in addition, the network is now balanced in that neither the decoder nor the encoder dominate the runtime. To the bottom left, we show a visualization of depth estimation performed with our model. The RGB input samples shown here come from the NYU Depth v2 dataset, which we used to train our fast depth DNN. This dataset is comprised of video sequences of indoor scenes, with depth measurements being on the order of several meters. We incorporate skip connections between the encoder and the decoder to help sharpen the depth map output and improve our model accuracy. We use additive skip connections, where we add the connected feature map channels instead of concatenating them. This lets us avoid incurring a computation overhead, keeping our model runtime the same. As we now see on the bottom left, with skip connections, our model produces sharper depth maps. That covers the neural network design of fast depth. There are two more steps that we take in deploying fast depth on the Jetson TX2. One of these is hardware-specific compilation. This is motivated by inefficient performance of depthwise separable layers on embedded devices, which is due to poorly optimized low-level operators in deep learning frameworks. This has spurred considerable research in compilers for DNNs that tune operators for specific hardware targets. In our work, we use the TVM compiler stack to optimize fast depth for the Jetson TX2. The compiler can be understood in two parts. The front end is what interfaces directly with the DNN model definition, and it transforms the model into a computation graph. This graph simply represents dependencies between operations and is hardware agnostic. The compiler backend takes this computation graph and performs hardware-specific optimizations. These can aim to reduce memory accesses, hide memory latency, increase parallelism, all with the overall goal of reducing model latency. At this stage, empirical measurements done on actual hardware may be taken into account to help guide the optimization process. Compilation outputs an executable that is tuned specifically for fast runtime on a given hardware target. In our case, that target is the TX2 GPU or CPU. On the bottom right, we now see that with hardware-specific compilation, our model runtime is halved even further. The last step in our design process is DNN simplification through pruning. This is motivated by trained deep learning models being often over-parameterized and containing operations that may be redundant. Pruning algorithms identify these redundant operations and remove them without noticeably impacting model accuracy. In our work, we apply the NetAdapt pruning algorithm as a final simplification of our fast depth network. In the chart shown mid-slide, the gray outline depicts the original network shape, while the colored bars show the effect of pruning on individual layers in the network. We note that the size of the layers, denoted by the number of input channels to them, is greatly reduced for many of the layers in the middle of the network. This means that the filter size for these layers is also shrunk, resulting in less computation and lower runtime overall. As a result of this simplification, our model runtime is further reduced by 1.5 times, and our total inference runtime is just 5.6 milliseconds per image on the TX2 GPU. Pruning has a negligible impact on our model's accuracy, and the visual clarity of the depth output is maintained, if not improved. When deploying on Jetson TX2, we compare against several prior works that are listed in the accuracy versus frame rate plot here. The quantitative accuracy metric used here is the delta-1 metric, which measures the percentage of pixels in the predicted depth output where the relative depth error falls within 25% of ground truth. The higher the delta-1 accuracy, the better. The y-axis here reports delta-1 accuracy. The x-axis reports frame rate on the TX2 GPU. The desired region is the upper right-hand corner, denoting high accuracy and high frame rate. which directly implies low latency since we run inference on just one image at a time. Our model, located far to the right of all other listed models, achieves comparable accuracy with over an order of magnitude speedup in inference runtime. Here we show a video sequence of depth estimations performed by our model in comparison with ground truth and with the baseline. This baseline corresponds to the model denoted by the pink dot in the upper left-hand corner of the accuracy versus trade-off plot. Lastly, we report the power consumption measured on the TX2. We measure power at inference time on both the GPU as well as on the CPU in isolation. On both platforms, total power consumption ranges around 10 to 12 watts, with active power consumption of 7 to 8 watts. This demonstrates that with our fast depth DNN, we successfully achieve real-time depth inference at under 10 watts of active power. We additionally deploy our model on an Apple iPhone. We target two iPhone devices, the iPhone 6s and the iPhone 10, that features dedicated neural network hardware called the Apple Neural Engine. On both of these devices, our fast depth model achieves real-time inference rates, with frame rates of up to 25 frames per second on the older iPhone 6s and up to 40 frames per second on the newer iPhone 10. We ran our app with the fast depth model live at the conference venue at ICRA 2019, where we originally presented this work. A clip of the recorded video is shown here. The conference venue featured several indoor scenes with barriers, walls, and people all serving as obstacles. A longer demo video is available at our Fast Depth project website. We're additionally interested in deploying fast depth on an embedded FPGA. One advantage of this step is the flexibility to design specialized hardware to run layers in the fast depth DNN. Specialized hardware is more likely to achieve higher energy efficiency when compared to more general purpose hardware like CPUs. Another advantage of this step is that it allows for joint co-design and optimization of algorithm and hardware. In our approach, when designing an accelerator for fast depth, we have the ability to revisit and modify the original DNN to better utilize our custom hardware. In designing an accelerator for the fast depth neural network, a prominent design consideration is that of reconfigurability versus performance. For instance, consider again the structure of fast depth. The encoder primarily uses filters of size 3 by 3, while the decoder uses filters of size 5 by 5. If we design an accelerator that is dedicated for 3 by 3 convolutions, how do we run the 5 by 5 ones on it? Making the hardware reconfigurable would incur area and energy costs. Designing a separate accelerator for 5 by 5 convolutions would also incur area and energy costs. In our approach, we actually revisit the fast depth DNN model definition itself to see if we can make any modifications there to address this design challenge. We'll recall that in the decoder, every upsample layer consists of a 5 by 5 convolution, followed by nearest neighbor interpolation. However, this means that the 5 by 5 convolution in each subsequent upsample layer will have its 5 by 5 convolution following the previous interpolation. As a result, there is some structure to this convolution that we can exploit. Suppose an interpolated feature map is fed into the 5 by 5 convolution of a subsequent layer, as shown here. If we superimpose a 5 by 5 filter from the convolution over the interpolated feature map, we know that the 4 filter values in the upper right-hand corner all apply to the same pixel value, in this case, a green pixel value. This means that in the convolution, all 4 of these filter values would get multiplied by the same pixel value. Instead of performing 4 multiplications and then summing them, we could first add the filter values and multiply once by the green pixel value. We can apply a similar step to the rest of the 5x5 filter. The windows of filter values that could be pre-added are shown in red here. By pre-adding these filter values, we can actually generate a smaller 3x3 kernel. In the end, we discover that the 5x5 convolution can be decomposed into a set of smaller 3x3 convolutions. This insight allows us to slightly alter our original fast depth DNN so that this decomposition can be better exploited. In our resulting model, every layer in the encoder and the decoder can run natively on an accelerator that is dedicated just for 3x3 convolutions. This was one example of a design consideration about the trade-offs between reconfigurability and performance. Another example concerns how the depthwise separable layers are themselves run on the accelerator. Recall that a depthwise separable layer consists of two operations, a depthwise convolution and a pointwise convolution. These two convolutions have different computation characteristics. Again, we must decide whether implementing reconfigurability to handle this is advantageous or not. While I do not have enough time to discuss this more in today's talk, if you're interested in learning more, we go into greater detail about the design process in my thesis on this work. I'd like to conclude by highlighting two key takeaways from this talk and from our work on fast depth. One takeaway is that in depth estimation DNN design, complexity is not necessarily better. Simplicity is not necessarily worse. We observe in our efforts to design a low latency depth estimation DNN that deeper networks with complex building blocks may achieve high accuracy, but at the cost of high model latency. Simplifying network designs, either through simpler layers or through pruning or through both, will result in faster models while lowering accuracy. But the accuracy degradation may be far outweighed by speedup gains. We observe with fast depth that we are able to achieve an order of magnitude speedup, with accuracy still close to state-of-the-art rates. Another takeaway is that hardware-in-loop optimizations are critical in meeting target goals. Examples include latency, power consumption, and utilization. We observe this with hardware-specific compilation that incorporates empirical measurements to guide its low-level optimization process. We observe this again when designing hardware for our fast depth accelerator, where our hardware design choices inform the modifications that we make to our fast depth algorithm. Optimizations that take hardware into account therefore prove critical for successful deployment on our embedded platforms. The evaluation code and the trained models from our fast depth work are made available at our project website listed here. I would like to thank Analog Devices, Intel, and the National Science Foundation for funding this work. And thank you to all for attending and listening to my talk.
Diana, thank you very much. I sent you the physical and the virtual clapping. So thank you for the very interesting talk. So participants, please raise your hand or excuse me, send a chat. Diana, let me lead off with a question though. First, a point of clarification. I think you made the statement that you're doing your estimation on a per frame basis.
Yes.
Okay. So what can you comment a little bit on what is the opportunity to use frame adjacency information so that if you have depth information from frame 1 and then you get frame 2, how do you use that frame 2? Is there a way to efficiently use that frame 1 as a prior to accelerate even further the estimation of depth in frame 2?
So there is research on this. We have not incorporated this in our work. There is research on using adjacent frames in a video sequence to not only increase like how much frames you're processing in the neural network at once, like increasing the batch size, for instance, but also to improve the accuracy of the depth output. There's also a matter of temporal consistency where you want depth in every frame to kind of correlate with some sort of scale, to maintain scale between different frames. So there is work on this. I have not incorporated this in the fast depth work that we published at the time, though.
Okay, thank you for that. Participants, please feel free to send me a chat to public or to raise your hand. I do have a follow-up question to my last one as participants sort of get their heads wrapped around what they would like to ask. Related maybe to the sort of video sequences, and recognizing that this isn't what you had focused on. I think you said you looked at up to 140 or 170 frames per second?
Yes.
So what is the sort of the balance between the energy consumption associated with higher frame rates and the computation to keep up with those frame rates? So there's energy acquired just to record fast imagery. You know, is there a trade-off, if you will, where you know, by the increasing power of your higher speed acquisition starts to become a detriment to overall efficiency versus using that time sequence? Yeah, sorry, go ahead.
Yeah, I understand your question. So the consideration here is that, do you actually need 178 frames per second? And if there's an application that requires that, the model will support that high frame rate, and it will run at the power consumption that we observed, so around 8 watts of active power consumption. If you do not need 178 frames per second, well, you're not going to be constantly running the model then. You don't necessarily need to. You can run the model for a smaller amount of time necessary to support whatever frame rate you're targeting. And then you're saving on power and energy consumption that you could then allocate to other tasks that are being performed on the computing platform. So if this would be part of a navigation system, there would also be other algorithms running alongside depth estimation. And so by supporting a higher frame rate, this enables us to use a lower frame rate if we need to, and instead offload, reallocate the power and energy resources that we have for other algorithms.
Very good, thank you. There's a question here from Alex. Have you quantified the cost saving between using a stereo setup with maybe a simpler CNN or DNN, or a monocular setup with your current architecture?
We have not explored stereo vision in comparison with monocular. For purposes of our work, we narrowed down into the monocular domain space and compared against work in that field. There have been works done on stereo approaches, but we have not directly compared against those.
Very good. From Santosh, could you comment on the maximum range of accurate depth measurements observed with the model?
Yes, so with our particular model, we train it on the NYU depth dataset, where all the scenes have depth measurements that are on the range of several meters. So as the model was trained, it will work pretty much on indoor scenes where depth is on the order of, let's say, 10 meters. It does not really work well outside because your depth ranges outside are on the order of tens, maybe hundreds of meters. In that case, you could explore either retraining the network on a different data set that's more representative of that environment, or use some transfer learning to, again, bring in, like, have the model kind of learn more about different scales of depth. But as it is, this model was trained and works on indoor scenes.
Good, thank you. There's a question chatted to me directly. I just saw one come in from Cedric, but let me ask this one first. Why not apply these energy efficient techniques on systems that don't require the energy efficiency? So if you were to look at a non-mobile system, is there something to be learned in terms of maybe having multiple instances of a very energy efficient algorithm in situations where you're not as power constrained?
Yeah, I'm sorry, I didn't fully understand the question.
So I think the question.
Scalability part.
So if you take an energy efficient algorithm that's designed to work on a mobile platform and instead run it on a non-mobile platform, or is there a benefit to looking at why isn't everything energy efficient? How can we sort of extend the energy efficiency to cloud-based or other server-based instances where you're trying to learn, but why not be energy efficient in those cases?
Well, for large like data centers, I mean, there are benefits of energy efficient design because that allows you, like you mentioned, to increase the number of instances you you run in parallel, which increases parallelism and throughput, and at the end of the day, lets you compute more. I guess in our work, we kind of focused on the reverse position, where it's much harder to take an algorithm that was, let's say, designed to run in real time on a server, on a large scale server, but it's much more difficult to fit that and run that in real time on a small device. Now, if you have something that you've designed for energy efficiency on a small device, if you were to run that on a larger scale machine, that just naturally gives you an increase in how much, like if you have the ability to instantiate it multiple times.
Very good,
I'm
thank
not
you.
sure if that answers the question.
I think so, and I think we have some related questions, also looking at implementation, I guess. Cedric asks, could you estimate how hard or long it will be to optimize your algorithms so they run on smaller microcontrollers, such as in the OpenMV project, Cortex M4, or other platforms, I guess would be the broader question.
Yes, so I mean, you would always start out with training your own neural network on some representative data set. And the steps you take into deploying it on a particular hardware target would, I guess, also depend on what that hardware is. If it's like a standard defined CPU or GPU architecture, I mean, there is ongoing work on different compilers that are supporting an increasing number of these hardware targets. And so you would want to compile specifically for whatever hardware target you are using. And that can take on the order of, I mean, in our project, it took on the order of several hours to maybe a day. But that's also dependent on the size of your network and how many layers there are in your network. If you are targeting more custom hardware, well, now you have the freedom to design your own custom accelerator, and that design process might take much longer, like on the order of weeks or months to develop and implement.
Thank you. I'll ask the last related question here from Anirudh. Thanks for the impressive presentation, they say. How does the fast depth network work with domain dataset transfer, apart from the NYU dataset, keeping in mind the trade-off between network generalizability and hardware reconfigurability?
Right, so network generalizability is the challenge. It was the challenge that it was something we left fast depth on, and subsequent work on this project might address this. We have tried running fast depth on images from other data sets, but obviously the performance is subpar, because if you apply transfer learning and retrain it on those data sets, you'll have much better model accuracy results. We have not actually tried we have not tried transfer learning with fast depth. That would be one of the next steps to make fast depth more generalizable.
Very good. Thank you, Diana. Let me just double check, make sure I'm not missing somebody with a hand raised. No, I'm not. Okay, so I think with that, Diana, thank you very much for the wonderful presentation and work, and for the questions and answers. I think the participants really enjoyed probing a little bit deeper here. So thank you again, and look forward to hearing more about what your next steps are for your career and your work. So again, everybody, thank you for your attendance and participation and questions. Do join us next week, same time, same channel, on Tuesday at 11 a.m. We'll hear from Michael Walsh on solid state platform for Boston Quantum Network. Again, Nano Explorations, an opportunity to engage with our phenomenal students. And we look forward to your continued participation. And Diana, again, thank you for your time and questions today. And everybody stay safe, and see you next time. Thank you.
Thank you.